Hi everyone! Today, we're talking about some common challenges in handling data, specifically in the transportation industry. Let's keep it simple and explore why dealing with data can sometimes be a bit tricky on the roads. Picture your data as a fleet of trucks. Over time, this fleet just keeps getting larger and larger. That's what we mean by data volume increasing rapidly. Too many trucks in the fleet can make things a bit confusing. It's like having so much information that it becomes a challenge to keep track of it all. Now, think of a big transportation company with different departments, one managing routes, another handling maintenance, and so on. Each department keeps its data in its own area. This is what we mean by data being scattered or dispersed. When data is all over the place, it's like trying to find a specific delivery truck in a busy parking lot, a bit challenging. Let's talk about how we gather information about our trucks. Some use a GPS, some use paper logs, and some use a special tracking system. Similarly, different departments might use different ways to collect their data. But using different methods can make it like trying to coordinate a convoy when the information doesn't match up. We want all our data to work well together. Now, what if you borrow some trucks from another company for a big delivery? That's like bringing in data from outside, maybe from other companies or sources on the internet. It's good to have extra trucks, but you need to be careful. You want to make sure they're in good shape and won't cause issues during the delivery. Okay. Now imagine you have different tools to manage your fleet, maybe a maintenance app, a route planning tool, or a fuel efficiency tracker. Choosing the right tool is important, right? The same goes for data in transportation. Picking the right tools to manage it is like choosing the best tool for maintaining and optimizing your fleet. You want it to be just right, not too big or too small. So, in a nutshell, handling data in the transportation industry is a bit like managing a growing fleet of trucks. We need to keep an eye on how many trucks we have, make sure they're not all over the place, use the right tools, and be careful when bringing in trucks from outside. It might sound a bit like organizing a fleet of vehicles, but managing data well helps transportation companies make smart decisions. That's what it's all about on the roads. Now, let's proceed with Data Flow Manager, also known as DFM, consists of the Decision Support System, Central Data Request, Data Integrity Component, and a vital link to our buddies outside the external data suppliers. Together, they're like the command center, ensuring our transportation system operates like a well-oiled machine. Now, let's explore the incredible functions of DFM. Consider having 10 trucks when you only need one for a specific route. DFM steps in to minimize data redundancy, making sure we don't have unnecessary duplicate entries for the same transport information. Think about different departments handling transport data separately. DFM prevents data isolation, bringing together information from maintenance, logistics, and more, ensuring a unified and efficient transportation network. Imagine receiving different route information from different sources. Not ideal, right? DFM acts like a unified GPS system, minimizing data inconsistency to provide reliable and coherent transport data. We all want our cargo and route plans secure, right? DFM acts as a secure vault, maximizing data security to ensure that only authorized personnel can access critical transportation information. Just as a well-maintained vehicle ensures a smooth journey, DFM maximizes data integrity, guaranteeing that our transport information is accurate and trustworthy from start to finish. Ever wanted to reroute a delivery without a complicated approval process? Data independence, facilitated by DFM, allows transportation teams to make timely decisions without always seeking permission, ensuring flexibility in managing our fleet. In summary, DFM is a team that's dedicated to making our transportation data management seamless.
Database Management System, a software system used to create and manage databases. It minimizes issues like data redundancy, eliminates duplicate data entries caused by manual transcription or multiple sources. Data isolation allows all departments to access centralized data simultaneously, eliminating isolation. Data inconsistency. DBMS streamlines transportation system data sources to ensure consistency and avoid conflicts. While DBMS maximizes data security by implements robust authentication and access controls to protect data from unauthorized access. Data integrity. It enforces data constraints to maintain accuracy and prevent invalid entries. Data independence. by minimizing coupling, DBMS allowing for flexible changes without impacting applications. Data hierarchy. Bit, binary digit, the most fundamental unit, representing a binary state, 1 or 0. Byte, a group of 8 bits, used to represent various data elements, such as vehicle IDs, statuses, or other attributes. Field, a single piece of information about a specific entity such as vehicle name, ID, location. Record, a collection of related fields representing a complete entity, example, a vehicle or shipment. File, table, a structured collection of records about a specific aspect of the transportation system as a vehicle file containing records for each vehicle. Lastly, database, a comprehensive collection of integrated files, serving as the central repository for all transportation-related data such as vehicles, routes, shipments. Designing a transportation database. Firstly, data model, a visual blueprint, often a diagram, representing entities, their attributes, and relationships. Then, entity, a distinct person, place, thing, or event in the transportation system such as vehicle, route, shipment. Then, attribute, a characteristic or quality of an entity such as vehicle ID, model and capacity. Then, primary key, a field that uniquely identifies each record in a table vehicle ID. Lastly, secondary key, a field that provides additional identifying information, but not necessarily unique as license plate. Database management systems in transportation efficiently organizes and manages vehicle, route, schedule, customer, and other data. It centralizes data storage, retrieval, and user tools for adding, deleting, accessing, and analyzing data. Online transaction processing, OLTP, enables real-time processing of transactions, crucial for transportation operations. For example, scheduling shipments, updating vehicle locations. Relational database model, well-suited for representing complex transportation relationships. Organizes entities into tables for efficient storage and retrieval, managing relationships through keys, assigning a vehicle to a route. Query language enable users to retrieve specific information from transportation databases and perform various operations on the data. There are 2 types. First is structured query language, SQL. It is standard language for managing and manipulating relational databases. Widely used in transportation for querying and updating information about vehicles, routes, shipments, and so on. Secondly, query by example, QBE. It is a visual approach using a grid or template for users to construct queries without extensive knowledge of SQL syntax. It allows transportation managers to easily find specific data such as shipments scheduled for a date, vehicles with certain capacities.
Normalization is the process of organizing a relational database to reduce data redundancy and improve data integrity. It ensures that data is stored in its most streamlined form, leading to minimum redundancy, maximum data integrity, and improved processing performance. Normalized data is when attributes in a table depend only on the primary key, facilitating efficient data management and analysis within an organization. Virtual databases, which consolidate multiple data sources into a single system, offer several advantages. These include lower development costs, faster development time, reduced maintenance, and a centralized point of access to a company's data. Additionally, virtual databases provide improved availability, greater flexibility, and enhanced data quality. Despite these benefits, proper planning and consideration of factors such as hardware and license costs are essential for successful implementation. A data warehouse is a repository of subject-oriented historical data organized for analytical processing activities. Its key characteristics include time-variant data, non-volatile data, relational structure, client-server architecture, and web-based access. Benefits of data warehousing include quick and easy access to data. End users can access data quickly and easily via web browsers because it is located in one place. Extensive analysis. End users can conduct complex queries and analyses on large volumes of data, uncovering patterns and trends that may not have been possible before. Consolidated view of organizational data. By centralizing data from various sources, data warehouses provide a comprehensive view of an organization's data, facilitating better decision-making. Document management is the automated control of electronic documents throughout their life cycle within an organization. Maintaining paper documents requires ensuring that everyone has the current version, establishing an updated schedule, providing security, and distributing the documents to the appropriate individuals promptly. Document management systems streamline workflows, provide added security, and enable increased collaboration, making them an essential tool for modern organizations. These systems save time, improve data security, and enhance business intelligence and decision-making. Data Mart is a small data warehouse designed for the end-user needs in a strategic business unit, SBU, or a department. They provide a more rapid response easily navigated than enterprise-wide data warehouses. There are two types of data marts which replicated, dependent. Data marts are the small subsets of the data warehouse, and standalone data marts are like a company can have one or more independent data marts without having a data warehouse. Next, data mining is a tool for analyzing large amounts of data. It derives its name from the similarities between searching for valuable business information in a large database. Data mining technology can generate new business opportunities by providing automated prediction of trends or behaviors and automated discovery of previously unknown or hidden patterns. Data mining tools can be combined with spreadsheets and other end-user software development tools. It also creates a data cube and then extracts data. Examples of data mining techniques include case-based reasoning, examining historical data for patterns, retrieving information from the internet or intranet-based databases, and using a specialized set of algorithms that sort through large datasets and express statistical rules. The data mining task includes classification, clustering, association, sequencing, forecasting, regression, and time series analysis. The data mining applications can be used in retail and sales, banking, manufacturing and production, insurance, police work, healthcare, and marketing. Then, an operational data store is a database for transaction processing systems that uses data warehouse concepts to provide clean data to the TPS. It brings the concepts and benefits of a data warehouse to the operational portions of the business. It is typically used for short-term decisions that require time-sensitive data analysis, provides detail as opposed to summary data, optimized for frequent access, and provides faster response times. Meanwhile, online analytical processing, OLAP, is a set of tools that analyze and aggregate data to reflect the business needs of the company. These business structures, multi-dimensional views of data, allow users to quickly answer business questions. OLAP is performed on data warehouses and marts. It also has two types, which are ROLAP and OLAP database implemented on top of an existing relational database, and MOLAP is a specialized multi-dimensional data store such as a data cube.
Numbers have an important story to tell, said Stephen Few. This quote encapsulates the essence of data visualization. In today's data-driven world, various visualization techniques are employed. Bar charts, pie charts, line graphs, and scatter plots are used. Each technique excels in specific scenarios. For instance, line graphs are ideal for showing trends over time. On the other end of the spectrum, we have sophisticated techniques like heat maps and tree maps. Tree maps display hierarchical data where size and color represent different dimensions. However, as powerful as these visualization techniques are, they are limited. A simple dataset uses a bar, but complex data demands a three-dimensional scatter plot or a parallel coordinates plot. Looking towards the future, the arena of data visualization will evolve rapidly. Technologies like virtual reality, augmented reality, and AI are emerging as powerful tools. They hold the potential to revolutionize our interaction with data. These advancements in data visualization will have far-reaching impacts across various industries. Specifically, it benefits healthcare and finance. In finance, traders can use real-time interactive visualizations to track market trends and make informed investment decisions. In conclusion, data visualization is a powerful tool that gives voice to numbers. It evolves with technology, refining our understanding. The future of data visualization promises exciting developments from our daily data generation.
Information technology is constantly changing, and data management systems capture, store, and analyze data to support decision-making. Geographical Information System, GIS, a computer-based tool for capturing, storing, integrating, manipulating, and displaying data on digital maps. Every GIS record or digital object has a location. GIS is powerful for geospatial data analysis and visualization because it uses spatially oriented databases. This technology is used in logistics, disaster response, urban planning, and environmental management. Visual Interactive Modeling, VIM. VIM uses computer graphics to show how management or operational decisions affect objectives like profit or market share. Interactive modeling helps decision-makers visualize and analyze scenarios, aiding strategic planning and optimization. VIM improves decision-making by offering a dynamic, visually intuitive platform for exploring options. VR is an interactive computer-generated technology that provides users with three-dimensional graphics. VR immerses users in a simulated environment with artificial sensory cues, making them believe it's real. VR allows immersive data exploration and analysis in data management. This technology could make complex datasets more engaging and intuitive. Specialized databases. Traditional databases adapt to modern business needs. MTDs combine current databases and marketing data sources for real-time personalization and targeted customer interactions, a paradigm shift. MTD's interactive capabilities allow real-time database updates, unlike classical warehouses and marts. Web-based data management systems. This trend combines data management and business intelligence with web technologies. Corporations centralize query, reporting, OLAP, and other tools on portals. Smart data warehouse search engines improve data warehouse operations and information retrieval in web-based systems. Clickstream data warehouses track website interactions to gain user behavior insights. As technology advances and data analysis becomes more complex, data management systems evolve. Businesses are using GIS, VR, and specialized databases to gain deeper insights and make better decisions. Web-based technologies improve accessibility and collaboration, ensuring that data management systems continue to shape business intelligence and decision-making.